Hi there. The following video will answer for you the Unit 3 higher AQA modular paper. You're required to have a calculator, absolutely essential, and the paper takes 1 hour and 30. The following formulae are given to you in the formula sheet on the front of the exam. Area of a trapezium, volume of a prism, volume of a sphere, surface area of a sphere, volume of a cone, curved surface area of a cone, and it also gives you the area of a triangle, the sine and cosine rule, and the quadratic equation. Okay, let's start straight away. Calculate the circumference of a circle with diameter 9 centimeters. The circumference, remember, is the distance around the outside of a circle, or its perimeter. Now, you need to know this. The circumference is given by the formula pi times diameter, or if you're given the radius, 2 pi r. The other formula you need to know out of interest, not relevant to this question, is the area of a circle, which is pi r squared. Okay, let's calculate. The circumference is pi times the diameter, which is pi times 9, and if you work that out on your calculator, you get 28.3 centimeters. So 28.3 centimeters is the answer to question 1. Question 2. Here is an expression, an equation, a formula, and an identity. Write down which one is which. Let's start with something easy. An expression is something containing numbers, algebra, and arithmetic, but with no equal sign. So an expression has no equal sign. The key thing about an expression is no equals. So this one here must be an expression. Now an equation is straightforward. We know an equation is something we solve for x or for any letter. We can get a solution to an equation. So an equation has one variable in it which we can solve, and up here there is one item here. This here is an equation we can solve. It's got one variable, so this must be an equation. An equation is something you solve. That leaves us with a formula and identity. Now a formula is something you use to calculate another variable. A formula usually has more than one unknown or variable in it, and in the above here we've got P is 2L plus 2W. There are 3 letters in this, so this is a formula. It's calculating P for us if we know what L and W is. So this is a formula. That obviously leaves this one here to be an identity. Just to explain how you spot an identity is always shown by 3 lines, which is different from an equal sign. But what it means is that for any value of x I put in to this side, I get the same number when I put in the same value of x on the other side, no matter what x. So the difference between an equation and an identity, just to point out, any x I can put in to both sides here and I'll get the same number. But here, there's only one value of x that makes this side equal to 5. So that's the difference between the equation and an identity. 3. Shapes are made from squares and semicircles as in above. The area of a square is S, the area of a semicircle is D, so this is clearly S plus D, and the area of this, if it was a whole square, would be S, and this is D, so the leftover area is S, take away D. Use the diagram that to show that 2D is less than S. Well, if you had S, let's just draw ourselves out what an S looks like. An S looks like a square, like as follows. And we know that if you take a D out of it, it looks like that. And if you take another D out of it, it would look like that. So we have some leftover area in here. So that shows us that the square is bigger than 2 lots of the semicircle. I.e., another way around of reading that is that 2D is less than S. 2D is less than S. Question 3. Write down the shaded areas of these shapes in terms of S and D. The whole square is S, 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 and S, and we're taking away a D here, that's a D, and we're taking away another D here. So the shaded area must be 4 lots of S, take away 2 lots of D. And question 3, part B, II, it wants the area of this. Well, just imagine this here, this shaded area here. If I brought that down in here, it would fill it up totally. And if I brought this here up here, it would fill that up totally. And I would be left with simply the area of a square, which is S. Question 4. 5 footpaths meet at O. O is this point here. D is due south of O. That means that D is exactly 180 degrees from the north line. Kate is at O and she's walking towards B. So Kate is walking along that path there. On what bearing does she walk? So this is a question about bearings. Just a quick recap on bearings. What are they? Well, they are an angle. They are 3 digits. They must be given in 3 digits. They are always measured from the north. From north. And lastly, they're measured clockwise from the north line. So we want to work out what direction or what bearing that Kate is walking along. So the angle measured from the north clockwise is that angle there. The whole angle here is 180, so Kate's bearing must be 180. Subtract this 80, subtract the 60, which would be 40. But a bearing must have 3 digits, so we write 0, 4, 0 degrees. It then says Ben is at B and he walks to meet Kate. On what bearing does he walk? Let's go back to our diagram. Let's use a different coloured pen for Ben. Ben is at B and he walks towards Kate. So he's walking along this direction. So what bearing is he walking along? Well, to get a bearing, you've got to measure from the north. So we're going to have to take a north line from B. And the direction Ben is going is given by that bearing there. Now, because that's a north line and it's parallel to that north line, we know that these two angles here must add up to 180. So if this one we said is 40, this one must be 140. And therefore the leftover one around the outside here must be 360, take away 140, which would be 220 degrees. So the bearing for Ben, therefore, is 220 degrees. That's already given for us in 3 digits. Then it says Frank is walking from A to O. So Frank is here and he's walking along this direction here. It then says when he gets to O, what angle clockwise, and that's boldened for us, does he need to turn to get to C? So he then wants to go along this direction here. Now let's think for us how what bearing is he walking along. Let's work out the bearing he's currently walking along. Let's draw ourselves a north line. And we're asking ourselves, what angle is that angle in there? Well, in order to work that out, what we could do is instead work out this angle here. And that angle there I could get by doing 360, take away all the other ones from here. So these add up to 180. So to get this one here, it would be 180 left over, take away 90, take away 40. So this angle here must be 180, take away 90, take away 40, which gives us 50 degrees. Given they're both parallel, this angle here must add up to 180, must be 130. So his bearing was 130. So bearing was 130. So let's just make it clear what we mean by that. From the point he was previously, he took a bearing of 130. But then to get to C, C for a bearing from north is this 40 plus 80. So C is actually on a bearing of 120. So when he gets to this point here, at O, what angle does he have to go clockwise to get back on the correct direction to get to C? Well, I know he could just turn 10 degrees anti-clockwise, but he's not allowed to go anti-clockwise. Instead, he's got to go all the way from the angle he's currently going on, which is this direction, all the way around to here. So the question therefore is, we know this angle here is 10. There's a 10 difference between the bearing he's going on currently and the one he wants to go on. So therefore he has to go all the way around the whole circle to get back to that point. So he must end up on a bearing of 350 degrees. A bit of a silly question, to be honest, because why would you turn the whole way around when you can just go 10 degrees anti-clockwise? Nevertheless, that's what they asked. Okay, Sally's buying a radiator for her bedroom. Her bedroom from the plan view from above looks like this. And here's the various costs of heating. And it tells us that the output heat is the volume in cubic meters of your room times 42. Well, let's just get our heads around what's going on here. The room is obviously three-dimensional. It's 4.2 across. It's 3.1 deep. But it's also 2.4 high. So it's it's a three-dimensional room visualized like a cuboid like that. So its volume is going to be 4.2 times 3.1 times 2.4, and we're going to get for that 31.248 centimeters cubed. So what's the heat output? The heat output for this room is going to be 31.248 multiplied by 42, and we're going to get ourselves 1312.416 watts. So the watts we need is 1312. Radiator A is no good, B is no good, C covers us, and it's got a cost of £220. So the cost of the most suitable radiator, that's what they asked for, cost is therefore £220. Question 6. Complete the table for the quadratic equation y equals x squared plus 2x from x is minus 4 to 3. So let's put in minus 3. We do minus 3 squared. Let's do minus 3 over here. Minus 3 squared, and then we add 2 times minus 3. Well, minus 3 squared is 9, and 2 times minus 3 is minus 6. So we get the answer 3 for that one. And when we put in 3, 3 squared plus 2 times 3, well, 3 squared is 9, 2 times 3 is 6, so we plus 6, and we get 15. Let's just plot this x with this y. Minus 4 with 8, there. Minus 3 with 3, there. Minus 2 with 0, there. Minus 1 with minus 1, there. 0 with 0, there. 1 with 3, there. 2 with 8, there. And 3 with 15, about there. And we draw a line in between. So our line would look something like this. A bit smoother than I've done it. A little bit smoother than I've done it there. That's not the greatest line ever. Okay, and hence we've completed our table. Use the graph to find the value of y when x is 1.5. All you do is you draw a line up from x is equal to 1.5, somewhere like here, probably a little bit over. X is 1.5 here, and you get a value for y. Y is about 5-ish. Y is approximately 5. My drawing is not accurate. In the mark scheme it says 5.2. So y is about 5 or 5.2. So using the graph, y is 5.2, let's say. you would have a much bigger diagram in the exam and it would be much clearer for you. Question 7. Use ruler and compass only. Show all construction lines and arcs. Construct the perpendicular bisector of AB. So AB is what's called a line segment. Here's AB. The perpendicular bisector is a line that cuts that exactly in half and makes a right angle with it. Now we can't just draw that in, we have to use a protractor, a sharp pencil and a ruler and a pair of compasses. So let's have a go at doing this. Firstly, let's take out a pair of compasses, and what we're going to do to draw the perpendicular bisector is we're going to put the compass on one end here, and we're going to drag out the pencil so it's past halfway. So it's just past halfway, and then we're going to draw an arc from that side there. Okay? Then what we're going to do, not adjusting the distance of the pencil as away, we're going to move the compass to the other side, to the point B, and we're going to switch the direction of the compass around, and we're going to draw ourselves another arc line there. Now, we're going to take that away. The points where they cross are going to be our key points here and here, and with a ruler we're going to draw a line segment between these 2 points. So with a ruler here we're going to try and draw a line segment between these 2 points here and see if it works for us. So something like that, and carefully we just draw in our line, and that is our perpendicular bisector. So that is at right angles. You could check, let's just check with our protractor if that actually turned out right. Is that a 90-degree angle? And looking at it, it's pretty spot on 90 degrees. And with a ruler we could measure that is about halfway between. So we've worked out our perpendicular bisector. (7b) Construct the angle bisector. An angle bisector is something that cuts the angle XYZ, this angle, into 2. So it's going to be a line that cuts that angle into 2. Again, you can't just draw it in, we've got to use compass and ruler. So let's insert our compass, and what we do for this is we put our compass on the point Y here, and we take out the compass to a certain distance. Doesn't matter how far, just take out that compass to a certain distance here. Okay. Then what we do, we put a little line here, and the same line, in fact we can drag it down so it cuts both line segments YX and YZ. Okay, then what we do is we move our compass to the points where the arc cross the 2 line segments, and here it doesn't matter about keeping the distance the same. Here we could move the distance out somewhat here. Let's move the distance out a little bit, and let's just change the colour of the pen just to make it look different. Now from this point here we measure a little arc here, we do a little arc from that point, and then we move the compass to the other place where the arc crossed the line YZ, and we keep in it the exact same distance, and we draw another arc there. Now from the point at Y to the point where these 2 arcs cross is going to make our perpendicular bisector. At that point we get our ruler out, and we draw a straight line between the 2. Let's do it in a green pen, and that would be our angle bisector in this case here. Let's just check, not required to do this, but let's just check with the protractor that I've roughly cut that angle in half? Well, the whole angle is about 72 degrees and half the angle is about 35, 36 as required. So that is a good perpendicular bisector there. So just to take everything away at the end, it would end up looking something like that. Okay, question 8. The diagram shows an isosceles trapezium. An isosceles trapezium means that side and that side are the same, which also means that that angle is the same as that angle at 75 and that angle is the same as that angle at x. It says work out the value of x. You know that angles in a quadrilateral add to 360, so we've got two x's plus two lots of 75, which is 150, must add up to 360. Take away 150 from both sides, 2x must equal 210. Divide both sides by 2, x must be 105. So the answer for this is 105 degrees. Work out the area of the trapezium. Well, the area of the trapezium is given to you in the formula booklet as a half. You add up the parallel sides a plus b, and then you times by how far they are apart the height. So the area of this trapezium is a half. You add up the parallel sides, 10 plus 14, and you times by how far they are apart, 7.5. Using your calculator, we get ourselves the answer 90 centimeters squared for that. Question 8c. Some of these trapezia are put together to make a regular shape. The diagram below is incomplete. How many exterior sides does the shape have? You must show you're working. Well, if you make a regular shape, you know with any polygon, the sum of the exterior angles, so this is an exterior angle, the sum of the exterior must add up to 360 degrees. Now, looking back at your diagram, if this is 75 degrees here, and that's 75 degrees here, you know the leftover, because an exterior angle is formed with a straight line, must be equal to 30. So the exterior angles are 30, so how many are there? Well, if you do 360 divided by 30, you get yourself 12. There must be 12 exterior angles. So there are 12 exterior angles. So that must mean that the shape has 12 sides. So the shape must have 12 sides by the same token, because each exterior angle is matched by one side. Another exterior angle, another side. So there are 12 sides to this shape. Question 9. Use trial and improvement to solve this equation to one decimal place. They've given you the first attempt. They've told you that if you put 3 in here and cube it and add 2 times 3, you get 33, which is too low. Before you go into decimals, you must find a whole number that gives you an answer that's bigger than 56. So obviously try 4. You work out 4 cubed plus 2 times 4, and you get yourself the answer 72, which is too big. Now you want to get 56, let's go halfway between, let's go for 3.5. You work out on your calculator 3.5 cubed plus 2 times 3.5. And you get the answer around 50. You get around 50, which is too low. Okay, so you go a little bit bigger, you go 3.6. So on your calculator, 3.6 cubed plus 2 times 3.6 again. And you get yourself around 54, again too low. So you have to keep going to your two highs. So 3.7 is going to be the obvious choice. You do 3.7 cubed plus 2 times 3.7 again. And you get yourself 58, which is too big. Now at this point, you have to try halfway in between the one decimal place that was too low and between the one decimal place that was too big. You have to try 3.65. So you do 3.65 cubed plus 2 times 3.65. And you get around, you get 55.9, which again is slightly too low. So now we've got enough information. Let's just state what we're saying here. At the point 3.6, we're low. At the point 3.7, we're high. And at the point 3.65, we're low. So the answer must be closer to 3.7. So the answer to this question here is 3.7 to 1 decimal place. Question 10. ABC is a quadrilateral. The angles A and B are in the ratio 1 to 2. So in particular, if the angle at A was, say, x, an unknown, the angle at B is twice that, so it would be 2x. Angle C is 30 more than B, so this angle here is whatever B was, and we've called it 2x, but 30 more than that, so 2x plus 30. And angle D is a right angle, so that's 90. It says work out the angles A, B and C. Well, inside the quadrilateral, angles add up to 360. So we've got this angle x, plus this angle 2x, plus this angle 2x plus 30, plus this angle 90, must add up to 360 degrees. X plus 2x plus 2x is 5x. 30 plus 90 is 120, is equal to 360. That was collecting like terms. Subtract 120 from both sides. You get 5x is equal to 240. And then divide both sides by 5 to get what 1x is. X is 240 divided by 5, which is 48 degrees. So therefore, angle A must be 48 degrees. Angle B is twice that, which is 96 degrees. And angle C is 96 plus 30, which is 126 degrees. If you check those all add up to 360, you'll get that in fact they do, so you can be confident your answer's correct. Question 11. Two radio stations at A and B, so A and B, pick up a distress call from a boat at sea. The station at A can tell you that the boat is between 60 kilometers and 80 kilometers from A. Now let's just do this. Let's deal with that fact in isolation first. 1 centimeter represents 10 kilometers. Now I don't have the right scale here on the computer, but let's just use a scale. I'm going to do something like this. So here's going to be my ruler, and I know that from point A, the distress call was between 60 and 80 kilometers. So what I'm going to need to do is I'm going to need to get out a set of compasses, pair of compasses, and I'm going to have to work out 6 centimeters because that's equivalent to 6 kilometers. So at that point there, I'm going to put my sharp edge on the point A, and I'm going to draw a boundary line to say that the distress call is slightly more than 60 kilometers. So I'm going to bring this back here. I'm going to bring my compass back here, and now I'm going to do the exact same, but I'm going to take it a little further to 80. So at this point A, put the sharp point at A, twist it around, and 80 would look something like that. Okay? So I know that this distance here is approximately 80, and this distance here is approximately 60. So the region we're interested in, the distress call happened in between these two. But you also know another fact from station B. Station B, it tells you that the boat is between a bearing of 50 and 60 degrees from B. So from the north line, we want to measure an angle of 50 from north and an angle of 60 from north. So I'm going to get my protractor. I'm going to twist it round appropriately so that it's in line with the north line. And I'm going to, where 0 is on the outside here, I'm going to measure an angle of 50 degrees, which is about here. And I'm going to measure an angle of 60, which is there. And then using my ruler, it's between that bearing there and it's between that bearing there. So approximately, where could this distress call have come from? The distress call could have come anywhere in between those appropriate bearings along here. So anywhere along that distance there. Now, it may not be quite like that when you draw it for yourself on a sheet of paper because I've got the scale slightly wrong, but that's the principle behind this. Okay, we're asked here to calculate the size of angle X. So we are going to use some trigonometry, right angle triangle trigonometry. This is our unknown angle. This is the opposite. The longest side is always the hypotenuse and the side beside the angle is the adjacent. We want to know this angle and we've got the opposite and the hypotenuse. So what formula does that for us? Well, the sine formula does that. Sine x is equal to opposite 4 over the hypotenuse, which is 10. So x must be the inverse sine of 4 over 10, which is 0.4. Make sure your calculator is in degrees mode and you should get the answer 23.6. So x is approximately 23.6 degrees. Okay, question 13. Two rectangles have the following dimensions. 2y, so this side here must be 2y, and this side here is 3x, so that side must be 3x. Another rectangle, this side must be 5x, the same as that, and that side must be 6y. It tells us that the perimeter of this smaller rectangle is 21, and the perimeter of this larger rectangle is 43. It tells us to work out what x and y have to be. Well, why don't we just state some facts about rectangle 1? So call this rectangle 1 and call this rectangle 2. Rectangle 1, its perimeter is 21. So if we add up the sides, we get 21. So 3x plus 3x is 6x. 2y plus 2y is 4y. We add these distances up and I must get 21. Using a similar idea with rectangle 2, well, if I add up these distances, I must get 43. 5x plus 5x is 10x. 6y plus 6y is 12y. And I must get the answer 43. So I've got myself two simultaneous equations, equations 1 and 2. To solve these, usually the simplest thing to do is make the coefficient, that is the number in front of either the x or the y, the same. An easy way to do this would be to multiply the whole of equation 1 by 3. And I would get 18x plus 12y is equal to 63. I could call that equation 3. Let's just rewrite for ease this equation, equation 2 here. 10x plus 12y is equal to 43. And that's equation 2. Now if I subtract these equations, if I do equation 3 subtract equation 2, 18x take away 10x is 8x, 12y take away 12y is nothing. I did that on purpose to eliminate the y. And 63 take away 43 is 20. So that gives us that x is 2.5 centimeters. So x is 2.5 centimeters. And to find y, you substitute back in one of the equations. So let's say equation 1. You put x back in, so 6 times 2.5 plus 4 times y is 21. 6 times 2.5 is 15. So 15 plus 4y is 21. So to get y, you take 15 off both sides. So 4y must equal 6. And y must be 6 divided by 4, which is 1.5. And I would encourage you in the exam to check that putting these values in does work, and in fact it does. Okay, question 14. Solve the following equal to 0, given your answer to 2 decimal places. Now, how do we do this? Well, we've got a quadratic because it's got an x squared. It's an equation because we've got an equal sign and it's equal to 0. Because the question asks us to work out to 2 decimal places, it suggests using the quadratic formula, which is given in your formula booklet. X is equal to negative b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. So I will get my solution x by working out the following. So let's just write everything out really neatly to avoid any mistakes. A is 2, b is the number in front of x, negative 5, and c is the number which is negative 5. I suggest for students who have trouble with the calculator to work out b squared minus 4ac first. B squared minus 4ac, well, that's minus 5 squared minus 4 times 2 times c is minus 5. Now, minus 5 squared is minus 5 times minus 5, which is 25. Minus 4 times 2 is minus 8. Minus 8 times minus 5 is plus 40. So these two things together would actually be 65. And now I can just straight away substitute my values in. So x on the one hand is minus b, minus minus 5 is plus 5, plus the square root of 65, all over 2a, which is 2 times 2, which is 4. Or x is the same thing, but with a minus square root 65 over 4. Type these two things into the calculator and we'll get the following. X is on the one hand 3.27 and I've rounded that to 2 dp. Or on the other hand, minus 0.77, and I have rounded that. When I got that, for example, out of my calculator, it was minus 0.76556. So to round it to 2 decimal places, I put a line after the second one. That's 5 or more, so I round that up to 0.77. Okay, question 15. 1,000 bacteria are put into a petri dish. After 1 hour, there are 2,000. And they continue to double in quantity after every hour. Draw a fully labelled diagram for the first 4 hours. So, when time is 0, you have 1,000. After 1 hour, when time is 1, you have 2,000. When time is 2, you double that and get 4,000. When time is 3, you double that and get 8,000. And when you've got 4 hours, when t is 4, you get 16,000. So we've got our t1 to 4 here. We've got to have a graph that goes up to 16,000. We've got 1, 2, 3, 4, 5, 6, 7, 8 squares. So make each one 2,000. So that's 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, 14,000, and 16,000. Okay, and then we just plot the points. When t is 0, you've got 1,000 there. T is 1, you've got 2,000. When t is 2, you've got 4,000. When t is 3, you've got 8,000. And when t is 4, you've got 16,000, which is somewhere up there. And you draw a line between these, a nice smooth line. That's an exponential curve that looks something like that. 15b, it asks you how many bacteria will be in the dish after 12 hours. Show your working. Well, let's just think. When time was 0, we said there was 1,000. When time was 1, there was 1,000, but then you doubled it. When time was 2, there was 1,000, and you doubled it twice, when time was 3, you had 1000 initially and you doubled it 3 times. So clearly when t is 12, just using this method, we're going to have our 1000 times 2, but it's going to be raised to the power of 12. We're going to double it 12 times. So type that in your calculator and you're going to get the answer 4,096,000. So that's how many bacteria there should be after the 12 hours as required. It does say, however, to give your answer to an appropriate degree of accuracy. Now, you were given all the original data to one significant figure, so I'd be tempted to round this to one significant figure. The first significant figure is in the millions column. What's the nearest million to this? Well, I would give the answer as 4 million, and I would state clearly that I've chosen one significant figure. Okay, Fred is marking a sector of a circle on a sports field as shown. He puts a tape around the perimeter. Tape comes in 3 meters rolls. How many rolls does he need? So we've got to work out the perimeter, which is this distance 40 plus this distance 40 plus this arc, whatever that distance is there. Now, let's work out the distance of the arc BC. Well, the distance of a whole circle, you'll remember, is 2 pi r. 2 times pi times the radius. So how much of a circle have we got here? Well, we've got 50 degrees out of a total of 360. So we've got that portion of a circle. And if we multiply that by 2 pi r, 2 pi and the radius here, r is 40, that would give us the arc length BC. So we type that into the calculator. And we actually get ourselves 34.9 for BC, and that's meters. So total distance is this 34.9 plus 2 lots of the 40, so plus the 80, and we get ourselves 104.9. How many 3 meter rolls do you need? Well, you need 104.9 divided by 3, which gives us the answer 38.3. You can't have 0.3 of a roll, so you're going to need to buy yourself in the shop 39 rolls. Question 17a. Here is a circle with centre O. Here's the centre. What is the value of x? Well, you should remember one of your circle theorems. The angle subtended at the circumference of the circle is half the angle subtended by the same arc at the centre. So x must be half 104, which is simply 52 degrees. 17b, here's a different circle. What's the value of y? Well, you should also remember that if you have an arc, then the angle subtended from an arc, from the same arc, is the same anywhere at the circle. So I am subtending an angle from that arc, and it's 28. Any other arc I choose, any other angle I choose that is also subtended by the same arc, for example there, must be 28. And in particular, this one here, y, well that's subtended from the same arc, so that also must be 28. So y is equal to 28 degrees. 17. ABCD is a cyclic quadrilateral with centre O. So here is the centre, and ABCD is a quadrilateral with its vertices attached on the circumference of a circle. It tells you various angles, and it asks you to prove that the line segment AB is parallel to the line segment CD. Okay, so let's fill in a bit of information that we already know. XY, it tells you, is the tangent. So angles on a straight line add to 180, so this angle here must be 180, subtract 58, subtract 78, which is 44. So this angle here must be 44 degrees. Now, using the alternate segment theorem, if this angle here is 44, this angle here must also be 44. And similarly, as that's 58, this angle here must be 58 degrees. Now, one other thing to say, angles in a cyclic, opposite angles in a cyclic quadrilateral add to 180. So this angle, together with this angle, must add to 180. So this, by default, must be 102 degrees. And similarly, this here plus this must equal 180. Well, this angle is 34 plus 44. And if we add that to the 58, plus whatever this unknown angle is here, we must get 180. So that unknown angle, rearranging this, is 180, subtract 58, subtract 44, subtract 34, which is 44 degrees. Okay, now let's just have a think about what we've shown. We have therefore shown the following. Imagine that line there, that's CD, and that's BA, and we've sort of created ourselves a Z angle, or an alternate angle. Now this angle here is 44 and this angle is 44. So therefore we know that this line must be parallel to that line. So how do we prove AB is parallel to CD? How do you say exactly? Well, we've done all the workings on the diagram, but we can say even more than that, that because angle ABD equals angle BDC equals 44 degrees, we can say that they are alternate angles, so AB must be parallel to CD. 18, the last question. We have ABCD, a quadrilateral, so a four-sided shape, and it tells us various distances and angles inside the shape. It wants us to work out the area of ABCD. Okay, well, an obvious way of trying to do that is to work out the area of this triangle, I might call that triangle 1, and add it to the area of that triangle, triangle 2. Okay, well, in order to do that, let's work out triangle 1. The area of triangle 1, well, we can use the formula in our formula booklet, which is a half AB sine C. Well, what that means is a half times 2 of the sides multiplied by each other, 7 times 8, and the sine of the angle in between those two sides, so the sine of 80. So you work that out and you get 27.6 centimeters squared. Now, how would you work out the area of triangle 2? Well, you would need to know this perpendicular height here, h. Okay? So in order to be able to work out that height h, you would need to first know this distance there, which is the hypotenuse of the right-angled triangle AC. Now, again, the formula booklet gives you what's called the cosine rule. It tells you a squared equals b squared plus c squared minus 2bc cos of a. And what this is saying, let's use AC to mean our little side a. It means that if I want to work out AC squared, then it is equal to the two other sides squared, so 7 squared plus 8 squared, we're dealing with this triangle here, minus 2 times 7 times the 8, 7 times the 8, and times cos of the angle opposite the side we're trying to find. So that's 80, cos 80. So that would get us that AC squared is, we type it in the calculator, 7 squared plus 8 squared minus 2 times 7 times 8 times cos 80, and make sure our calculator is in degrees mode, we get AC squared is 93.55. So we know now this side squared. We know what AC squared is. So if we want to work out h, We can use Pythagoras' theorem because we've got a right angled triangle here. I'll just redraw it out for you. We know that side is 6. We don't know that side h, but we know that AC squared, this side squared, is 93.6, 93.55 even. So we could work out h squared. H squared must be the hypotenuse squared, 93.55, subtract the shorter side squared, subtract 6 squared, which is 36. So work that out, and you get that h squared is 57.6. So h is the square root of 57.6, which is 7.6 to one decimal place, 7.6 centimeters. So what's the area of triangle 2 now? Let's rub this out here. What's the area of triangle 2? Well, area triangle 2 is half the base, half times 6 times the height we've got is 7.6 or 7.58. I've got that to more accuracy, and we get that to be 22.8 centimeters squared. So the total area must be this area plus this area, so 27.6 plus 22.8. Work that out, and you get an area of 50.4 centimeters squared. Thank you for listening to this video. I hope you found it useful in your revision for Unit 3.